It is time to denoise images. We're about to develop a series of such algorithms, and we start with something really simple. We kept saying that P0 epsilon is the core engine of SparseLand, and so it seems like a proper place to start from. Given the noisy image Z, we should seek the sparsest representation alpha to explain it up to an epsilon error. Once computed, we should take this representation and multiply it by D, and this will be the denoised image. Sounds quite simple, but we need to make few decisions. Who is the dictionary D? How do we set epsilon? And how shall we approximate the solution of P0 epsilon? Observe that all these questions already came up in the context of the image deblurring task we discussed. In order to keep things as simple as possible for the beginning of this chapter, we will make similar decisions here. Thus, we will choose the redundant Haar as D. The epsilon will be simply the level of the noise we expect in Z. As for the algorithm, we could suggest ISTA all over again, but we'll do something even simpler than that. We will suggest the thresholding algorithm. This means that the noisy image will be correlated with the atoms in D, and small values will be nulled. Then we will multiply back by D, and that's it. Observe that this could be interpreted as the first iteration of ISTA if the initialization is the zero image. Just before we turn to experiment with the above algorithm, there is a delicate matter that needs to be taken into account. D does not have normalized atoms, and this implies that in the thresholding operation we cannot use the same threshold for all the atoms. The remedy we suggest is quite simple. We will use a threshold that is linearly proportional to the norms of the atoms. If these norms are stored in a vector W, then we will compare the inner products to T times this vector and threshold based on this. T itself is a parameter that we will tune manually for best results. By the way, you must be wondering how come we did not take these atom norms into account in the deblurring? The answer is simple. We should have, and the results would have improved a bit if we would have done so. Just before we run the algorithm, we have to say a few words on this experiment. The image Barbara with noise level sigma equals 20 will be used to test the performance of this and later algorithms. The quality of the result will be measured by peak signal to noise ratio, as given in this expression. In the denominator, we compute the L2 error between the resulting image and the ideal one, and thus the bigger the peak SNR value, the better the result. And here are the results. The blue curve in this graph shows the peak SNR as a function of the threshold scalar T. The red line stands for the peak SNR of the noisy image. The peak value we get is nearly 28 dB, which is not bad at all. This is obtained for T equals 53. Could we suggest a way to find this value automatically? The answer is partially positive. This graph shows the per pixel residual value as a function of T. As T grows, the residual grows with it. When the residual is 20, we remove the proper amount of noise from the image, so this would be a good value of T to use. Such a residual value is obtained for T equals 64. Not a perfect prediction of T, but a reasonable one nevertheless. And here is the result itself. We see the original image on the left, the noisy one in the middle, and the restored one by our algorithm on the right. Zooming in, we see some artifacts and over-smoothing, but I have to say, this is not bad at all, and especially so considering the stupid algorithm we have just tested. If anything could be concluded from this experiment, then it would be that there is a great hope for much better results as we make our algorithm more sophisticated. Let's summarize this part. The global thresholding algorithm, crude as it may be, is working fine. However, fixing T is still a challenge. When using the residual to drive the choice of T, we drop by nearly 1 dB. Could we do better than that? The answer is yes, as you are about to see. Another complication is the same one we encountered in the deblurring test, and this should not be surprising since the two methods employed are quite similar. The algorithm we use could lead to a sparse representation if T is chosen high enough. However, the ideal value of T leads to a rather dense outcome. This again calls for some explanations.